I know I've been saying for weeks that I was going to do this, but we're going to do it now. We're going to look at the anatomy of Horner's syndrome. Horner's syndrome is useful for you because it's a series of signs that you see in the face, in the eye, on one side of the body that can clue you into something that's going wrong in the chest or in the neck or maybe centrally in the central nervous system. So we need to talk about what Horner's syndrome is, and then we need to look at the anatomy of Horner's syndrome. It involves the sympathetic nervous system and how sympathetic neurons get from the chest to the eye, but we'll consider the whole route. And you need to know the anatomy because there are a number of things that can affect it. And if you know the anatomy, you can work that stuff out. Honestly, it's a really long list of things. If you do a big long list of things, it won't make sense. The anatomy will make sense, all right? Anatomy, we'll do it. Yes, there is a creche behind the anatomy lab, and yes, they too tend to go quiet about the time I stop filming. I don't have the luxury of a studio or time, I have to get stuff done. Anyway, so enjoy. We were teaching pharynx and larynx this week, and two of the ENT surgeons said that they prepared for their teaching by watching my videos. It's kind of terrifying. In Horner's syndrome, you will see in the eye meiosis, that is constriction of the pupil. So one pupil will be more constricted than the other pupil. You will see partial ptosis, that is a drooping of the eyelid, not a massive drooping, just a little drooping of the eyelid, partial ptosis. And you may see anhidrosis, that is a loss of sweating or reduced sweating on one side of the face relative to the other side of the face. All of those things are controlled, driven by the sympathetic nervous system. You might also see some reddening of the conjunctiva. It might look like the eyeball is sunken. If you measure it, it's not, but because the eyelids have changed a little bit, it might look like the eye is sunken on one side. And the lower lid might be a little bit swollen or elevated. What do we mean by the sympathetic nervous system? Nervous system, okay, so we can divide the nervous system into somatic and autonomic. Somatic is of the body, is the stuff that you can think about and it happens. So for example, skeletal muscles are under somatic control. I can think about moving my arm moves. Also, if I poke my skin, I'm aware of that sensation. That's all somatic sensory stuff coming in. So the autonomic nervous system is the stuff we're not aware of. It's the automatic stuff. And it also has motor and sensory components. Now the motor components are sympathetic and parasympathetic, largely. And the sympathetic nervous system is your fight or flight system, and your parasympathetic system is your rest and digest system. Often they work in opposition, but often they don't. The sympathetic nervous system is motor. It's driving something. It's driving smooth muscle or cardiac muscle, generally speaking. So the sympathetic nervous system will cause your heart rate to increase. It'll cause your heart to beat more forcefully. It'll cause your hairs on your skin to stand up on end. It'll cause a change in the direction of, or the change in blood flow around the body, so you have more blood going to your muscles. So you're a supercharged little superhero furry mammal that will hopefully survive this encounter and learn from it, so you can have more little baby furry mammals in the future. That's your fight or flight response, and it's adrenaline and noradrenaline mediated at the target organ end of things. And the sympathetic nervous system will control the blood flow to your skin. So if you're hot, more blood will flow to your skin, so you'll lose heat. And it'll innervate your sweat glands, so you produce sweat, so you can cool down. It'll also cause your pupils to dilate, and it'll cause your eyes to open widely. We're seeing some links back to where we started, aren't we? My eyes are drying out. So sympathetic nervous system drives those things we were talking about related to Horner's syndrome. Okay. Most of those autonomic functions we were talking about are driven, if we're thinking about the brain, they're driven by centres in the hypothalamus and in the brainstem, right? Which means there must be neurons running from those centres out to the target organs. And if we're talking about the skin and hairs standing up on end and blood flow to the skin and sweat and stuff, that means that the sympathetic nervous system has got to go absolutely everywhere in the body. It's got to go everywhere. And what we see is, we see neurons travelling from the hypothalamus and the brainstem down the spinal cord, and we see sympathetic neurons coming out of the spinal cord at thoracic levels, at L1, L2 and maybe L3 levels, but only those levels. So the sympathetic, okay, we've got some terminology issues going on here as well. Anatomically, we talk about this as a 2-neuron chain, but in total there are 3 neurons. If you think about, there's a neuron running from the hypothalamus or the brainstem down to the spinal cord. It meets a second neuron that leaves the spinal cord, which meets a third neuron and goes off to the target structure. Anatomically, I talk about a 2-neuron chain. When you're talking about Horner's, you might talk about a 3-neuron system, and I'll come back to that at the end. But let's just think about our 2 neurons. All right, spinal cord, grey matter and white matter. We see in the thoracic levels of the spinal cord, in the grey matter, we see a lateral horn, like a little pointy bit. And in that lateral horn, that's where we find the cell bodies for the preganglionic sympathetic neurons. That's like the first neuron that's going to run out of the spinal cord. And because in the spinal cord, all motor neurons run out of this ventral root here, those preganglionic sympathetic neurons will run from the lateral horn out through the ventral root and into the spinal nerve, but they don't have very far to go. If I take this model apart a little, we can see what I'm talking about. This is the back of the thoracic cage. We've got the esophagus in here and what have you. And these yellow things here, these are collections of preganglionic sympathetic neurons, and they're running out to these structures here. This arrangement of nervous structures on the posterior thoracic wall, this is the sympathetic chain, the sympathetic ganglion, the sympathetic trunk, the paravertebral ganglia. We got lots of names for them. But if I've been calling these first neurons that leave the spinal cord preganglionic sympathetic neurons, you can see why now. Those preganglionic sympathetic neurons will run out to a sympathetic ganglion, and in that ganglion, so a ganglion is a collection of nerve cell bodies, the neuron, its cell body is in here, and the axon of those neurons will then run out somewhere. So the preganglionic sympathetic neuron will run to that ganglion, synapse and connect with a post-ganglionic sympathetic neuron, which is then going to run away from there. And from there, it's going to travel the entire distance to your big toe, to your eye, to the top of your head, to your fingertips, whatever. There is more to this. We don't just see these sympathetic ganglia at the thoracic and L1, L2 and L3 levels, which are the levels that we said the preganglionic sympathetic neurons come out of the spinal cord at. We see more sympathetic ganglia extending up into the neck, down into the abdomen and down into the pelvis. So what happens is that some of these preganglionic sympathetic neurons run out to the sympathetic trunk and they pass down a few levels, or they might pass up a few levels to a different level ganglion, and then they synapse and then they run off to their target organ. All right, so the sympathetic trunk, the sympathetic chain, is longer than just T1 to L2 or L3. Pretty cool. All right, how do those postganglionic sympathetic neurons get to their target structures? Well, they can take a number of routes. One of their favoured routes is to jump onto a big blood vessel. Remember, we said they control blood flow through the body, so they're going to innervate the smooth muscle in arteries, in arterial walls, for example. So whenever I'm dissecting in the neck, I'll get down to the common carotid artery, the internal and external carotid arteries, And what I find is this beautiful, like lacework filigree, these tiny fibres running over and around the surface of those arteries. So the postganglionic sympathetic neurons run with the arteries to get to wherever they've got to get to in the body. And that's how they get into the head. And that's how they get to the eye. We're getting there, right? Look at the level we're at here. Here's the thyroid cartilage. Here's the brachiocephalic vein, brachiocephalic trunk. Right, if I take that off, okay, we can see some of the cervical. Maybe this image is more useful at showing you those cervical ganglion. So the sympathetic neurons we're interested in today run up to the superior cervical ganglion, and then up at that level, this is the common carotid artery running up here. And just as we get to the mandible, it divides into internal and external carotid arteries. The external carotid artery is going to run to the face. The internal carotid artery is going to run inside the skull. If you palpate your pulse up here, high in the neck, because these arteries are protected by muscles the rest of the way, if you get up here, you're feeling the pulse usually of the external carotid artery. So, our sympathetic neurons have jumped off onto these massive blood vessels, and the ones we're interested in are following the internal carotid artery into the skull. How do they get into the skull? How does the internal carotid artery get into the skull? Skull time. All right. Internal carotid artery. So if we look on the right side here, the internal carotid artery enters the skull, passes into the cranial cavity by running into the carotid canal. So it's a proper tube running through. It makes this gorgeous shape. It just, right? So the artery, the internal carotid artery runs in, and then it runs anteriorly in this tube and then superiorly. So if I take the calvarium off and try not to pull his mandible off, come on, boyo. There we go. You can see there's the internal carotid artery appearing there. There's this fantastic groove. So the bones and the blood vessels all develop together, right? So there's a groove in the floor of the skull. And that groove is there because the internal carotid artery is running within it. And the internal carotid artery runs to here. There's a fantastic curve around here, which shows, you can see it on that side, which shows the impression left by the internal carotid artery. Because, of course, this is just a skull and we've taken everything else out, and I've just put a pipe cleaner back in and pretended it's the internal carotid artery, but you get the gist. But look, because that internal carotid artery ran anteriorly and then superiorly, look where it's put itself. It's put itself perfectly posterior to the orbit. And inside the orbit, we have the superior orbital fissure, which lets all sorts of things from the cranial cavity to jump through into the orbit. And that is how our sympathetic nerves jump from the internal carotid artery and into the orbit and get to the structures of the eye. So what structures of the eye were we talking about? Well, we said the pupil on the side that's affected by Horner syndrome is constricted. It's smaller than the other one. So the muscle that dilates the pupil is named very sensibly dilator pupillae. So the dilator pupillae muscles are innervated by the sympathetic nerves. And then we said that the eyelid had partial ptosis. It was drooping a little bit. That's because the muscle that lifts the eyelid, levator palpebrae superioris, has a small segment of smooth muscles within it called the superior tarsal muscle. Smooth muscle fibres. So those smooth muscle fibres of the superior tarsal muscle are innervated by the sympathetic nerves as well. So if at any point along that route that we've just described, those neurons have been crushed, severed, squashed, stretched, damaged in some way, that means that the innervation to dilator pupillae and the superior tarsal muscles could be lost. And likewise, I already said that the sympathetic nerves innervate the sweat glands in the skin. That's why we'd see a loss of or reduced sweating on just the one side. And that's the key thing about Horner's. It's only happening on one side, the same side as the injury. So the final question, what could cause damage to the nerves that we've described and lead to Horner syndrome? Well, we were talking about the brachial plexus, and we were talking about a lower brachial plexus injury, Klumpke's palsy, and how that can, if it was injury close enough to the spinal cord, that could damage the preganglionic sympathetic neurons that are coming out of the spinal cord. That would lead to Horner's. We often think of a tumour forming in the apex of the lung. That's up in the right place, up here. So a tumour forming in the apex of the lung. Remember that inside the body, everything's already jam-packed in there. So if you've got something growing in there, it's going to start crushing things and squashing things. So a tumour in the apex of the lung can compress those parts of the sympathetic nervous system that we were talking about and cause Horner syndrome. Likewise, a tumour in the thyroid gland could do that, or thyroid surgery could injure some of those sympathetic structures. The sympathetic neurons are following the arteries, so an aneurysm where the blood vessel swells and dilates, or a dissection of one of those major arteries could stretch those little delicate sympathetic neurons and damage them. In fact, trauma to the neck, whiplash, a penetrating injury, all sorts of things in the neck could damage some of those sympathetic neurons. Inside the skull, so up in here, that internal carotid artery is running through a venous plexus, a venous space called the cavernous sinus here. So thrombosis of the cavernous sinus can also compress those sympathetic fibres and cause Horner's syndrome. And then we said that those fibres are coming from the hypothalamus and they're coming from the brainstem. So ischemia, a blood clot, blocking the flow of blood to the brainstem or to the hypothalamus could lead to this. Or a tumour in the brainstem, or a tumour elsewhere causing compression of part of the brainstem, which is generally a very, very bad thing, could cause Horner syndrome. So do you see why understanding the anatomy is so important? If you understand the anatomy and you see the signs of Horner syndrome in a patient or somebody, it's not clear what the cause might be, but you can work out what the cause might be. You work your way through those things. You look for other signs and symptoms, don't you? And you don't treat the Horner syndrome, you treat the thing that's causing the Horner syndrome. And sometimes it is just idiopathic. And it's just kind of one of those things and there's not a big problem there. But sometimes there is. Right, have some more terminology. So I said anatomically we think of this as the sympathetic nervous system as a 2-neuron chain, that preganglionic sympathetic neuron and then that postganglionic sympathetic neuron. But we've also talked about the central part of that. So you could hear about Horner syndrome as central Horner syndrome. That means that the neurons in the central nervous system have been affected. You could read about preganglionic Horner syndrome, which is that preganglionic sympathetic neuron has been affected. Or you could read about postganglionic Horner syndrome, which is that much longer postganglionic sympathetic neuron that's working its way up to the head and the eye that's been affected. And those might also be referred to as first order, second order and third order neuron Horners. I hope that makes sense. I know in anatomy we try to be clearer and use contemporary terms and language, but this is medicine, and medicine is muddier than it's just anatomy, unfortunately. And it's biology, right? We're all different. So you might have noticed something a bit different this week. This is a sponsored video. Kenhub have been helping me out, helping me describe this topic by letting me use some of their images. If you've searched for anatomy on the internet, and I know you have because that's how you got here, you've already come across Kenhub. They've got over 700 articles, which I believe they're all freely available. The writing in their articles is accurate and detailed. And when I'm looking through these, I tend to find they've come across the same up-to-date information that I found in research papers when I've been preparing for a topic. Their illustrations are lovely, which is so important in anatomy to help you understand what it is we're made of. They include radiology and histology, so you get anatomy from the ultrastructure up to the gross structure. There being so much anatomy out there, another really important thing is the search engine, right? There's a huge amount of information on their website. The search engine lets you find it. So you can see what Kenhub have got to offer very easily with their hundreds of articles, and if you like what they do, you can pay for a subscription, and with that you get access to 500 quizzes. You can custom create your own quizzes for the areas that you need to quiz. They've got thousands of illustrations and they've got over 100 hours of video. Have I got more than 100 hours of video? Maybe. And on top of that, you get access to what they describe as an anatomy geek. You can ask that person any question about anatomy. They'll help you with your study. They'll describe topics to you. They'll explain things. They'll generally support your learning. They've also been producing charts of the muscles for the body. There's a lower limb one available for free if you set up a free account. And that's Horner syndrome. And that is some complex, detailed anatomy. And you can see how understanding that structure is the only possible way you could describe what's going on. And beyond that, use what you see to work out what the problem is, if there's a problem there. All right, and I hope the illustrations helped explain that this week, because nerves can be a difficult thing. Right, see you next week.